Welcome to the advertisement for our talk, Learning Formulas in Finite Variable Logics. My name is Paul, and this is work with Madhu Parthasarathi at the University of Illinois. This work is about supervised exact learning in the context of logic. So the idea is to learn logical concepts from examples that are first-order structures, and the hypothesis space is the formulas of some logic. So why look at this problem? 2 points of motivation. The first is that there are many kinds of data in the world that have some first order structure. Some examples include objects and relationships in images, pointers between locations in a heap, constructors and destructors for algebraic data types, program states more generally, and relational databases. And 2, we want machine learning artifacts that we can interpret. So they should have some clear semantics, which relates to the structure in data. So this work then is about learning logic formulas from example structures. What does this look like? So suppose that you're given these 4 structures. They are just undirected graphs. So they have a single binary edge relation E and 2 constants S and T. And the 2 structures on the left are labeled positive and the 2 on the right are labeled negative. Suppose also that you're given some grammar. So this is just regular first order logic in the appropriate signature. And now your goal is to find a sentence from the grammar that's true on the positive structures and false on the negative structures. There's probably many solutions, but the one I have in mind is the following. It says, for all x, if there's an edge from S to X, then there's some Y such that there's an edge from X to Y and an edge from Y to T. So it's pretty easy to check that this sentence is indeed separating the positives from the negatives. So over here, the leftmost positive structure, you see there are 2 edges out of S, and in each case, they can get to some Y, and that Y has an edge to T. And trivially, this is true for the second positive structure because there are no edges out of S. And similarly, it's not hard to check that this sentence is false on both the negative structures. So now we can also look at this kind of problem in a richer logic. So consider these structures. Now, after staring at it for a bit, you might have the idea that concepts like reachability in a graph and cycles might play a role. And that is indeed what I have in mind. You may also know that in first order logic, you can't express things like reachability in cycles. So we need to suppose that we're searching over a richer logic that can express these things. For instance, first order logic with recursive definitions. And in such a logic, one possible solution could look like this. So this says, let reach be a relation defined in some way over here. And then having that definition, it says for all x, there exists a y such that x reaches y and y reaches itself. Or in other words, every node can reach a cycle. Please attend our talk to hear more about this kind of problem. Those 2 examples were for the problem of learning separators, but we also looked at 2 other problems. One of them was learning queries, and the other learning logical terms. It turns out that all 3 of these problems are actually decidable for many different finite variable logics. Finite variable logic is what it sounds like. It's a logic where you can only use a fixed number of variables. The solution involves tree automata that read formula syntax trees and evaluate them against a fixed background structure. Our talk's on Friday at 4:40 p.m., and I hope you'll attend. Thank you.